Hello, in our final chapter here. And I'm actually here to tell you more lies. Well, not really lies, it's just mostly true. So, again, this is the what I'm talking about here. This is a model for the way things are. So, and we're still exploring more. We don't understand everything about it, but we understand it pretty well. And the models here work pretty well. So the model I'm going to talk about today is called VSEPR, sometimes called VESPR, but not really. But it's valence shell electron pair repulsion, and this was in direct competition with a theory we'll talk about later on this chapter called molecular orbital theory. It turns out that these two competing theories predicted different things, and now we were able to definitely say molecular orbital theory is the correct model. VSEPR is the incorrect model. So actually this model is incorrect. So why am I teaching something that's incorrect to you? Because it works most of the time. It's a very, very powerful model. It's fundamentally flawed, which we'll talk about later. And people were so bummed out that VSEPR was wrong because it makes so much sense. And I will show you. I will show you how this makes so much sense. And like I said, most of what I'm going to talk about today is true. So it works very, very well for vast majority of everything. So let's see here. Valence shell, so outside shell, electrons, pair repulsions. So outside electrons repel from each other. That's what this is saying. So the outside shells. So let's look at the geometry. So let's pretend like we have a chemistry dance club, and here is our dance floor. And let's say we have someone in the center, and we have two other people dancing with that person. The rule is that they are both really attracted to the person in the center, but they are utterly repulsed by each other. So they want to bond to the center, but they want to be as far away from each other as possible. What happens? Forms a line. We have linear geometry. So, and the reason for that is, so if you have these two groups that don't like each other, and the bond in the center, if they start moving close to each other, their electrons repel. So it forms linear geometry with a bond angle of 180 degrees or pi radians if you're into radians. So here's carbon dioxide, also has linear geometry. So what about if you have three people on the dance floor? What happens? Forms a triangle. So, and we're still planar, so we have these trigonal planar geometry. So boron trifluoride, three things, all the same. They have a perfect 120 degrees, that's 360 divided by 3, or 2 pi thirds radian, if you want to do the radians. Okay, so now comes into some of the finer points of theory. Oxygen has these lone pairs on them, so I'm going to give them these big chevrons of, I'll give them these big areas of electron density. So oxygen has these big areas of electron density, and what does it do? It pushes the hydrogens in a little bit. So that's where you have the distorted geometry then. So formaldehyde here has those, oxygen has those lone pairs, and it pushes those hydrogens in a little bit, changes the bond lengths. Okay, so what about four people? Four people form the tetrahedron. So you'll have, so if you have a center atom, you have three that crouch down, and then you have one on top, like so. So our dance floor metaphor breaks down with a tetrahedron because it's no longer on a plane. Plane means flat area. Now we've gone into the three dimensions, and now we have the tetrahedral geometry. So here is a tetrahedron, and has the ideal bond angle of 109.5 degrees, about that. I don't know what that is in radians. Whatever it is in radians, I can't do that math in my head that fast. So I mean, so uh, but methane. Methane has a perfect tetrahedron. What about here? We have nitrogen, and nitrogen and ammonia has four things around it. It has a lone pair and three hydrogens. In this lone pair, what happens is that density pushes the hydrogens down and changes the bond angle. So water also has tetrahedral geometry because it has two lone pairs, and we draw it. You can draw it this way. You think it's linear, but it's not. So this is also known as a Fisher projection. So think of it as two V's. So kind of scissoring together like this, right? So two V's, your finger, and then turn them 90 degrees together like that. And that is how the tetrahedron, that's how this Fisher projection works on the with the Lewis structure there. So actually these bond angles are like tetrahedra, and with the lone pairs, those two lone pairs push the hydrogen atoms in a little bit, and it has distortion there. But now you can see here that with no lone pairs, you have a perfect tetrahedron. One lone pair, it distorts the bond. Two lone pairs distorts it a little bit more. So that's the valence shell electron pair repulsion. So these are pushing that in more and more. Okay, so we've had four things. Now what about five things? Expanded octet. We did this last lecture with the phosphorus pentachloride. We have this geometry here, trigonal bipyramidal. So the idea is that you have here in the plane, and these are known as the axis. We have an axis there, so we have that in plane, and then we have, axial. The equatorial. The equator there is on the circle and the plane, and then the axial are along the above and below. So that's the this is the geometry here, and in the plane it's a 120 degrees. So circle divided by 3. And then the axial part, above and below, that's just, it's perpendicular. So if you know your geometry, if you have a plane and you have a bisector that's perpendicular to the plane, so all angles to this plane is 90 degrees. So it is that line of chlorines to the phosphorus, and the axis is perpendicular to the equatorial plane. Okay, and the lone pairs, so because of that, when lone pairs add to this geometry, they add to the equator. Okay, they don't add to the axial part. Why? Because of the 120 degrees. That's the furthest away. So adding one lone pair to it adds the equator, and this geometry is known as a seesaw. So if you remember a seesaw, kind of like the old seesaw when you're a kid and you're playing seesaw. Oh, that person's a little too low. So if you remember the seesaw from your youth going up and down, that's the same idea as that geometry. And then if you have two lone pairs with the bipyramidal geometry, this is known as T-shaped. So this is T-shaped molecular geometry. So if you notice, there's a difference here between electronic geometry and molecular geometry. The electronic geometry describes electron groups bonding and non-bonding, and the molecular geometry just describes the bonding groups. So it's T-shaped, but it's a weird T. It's like a T with a flat top. And then for three lone pairs with this electronic geometry, it's a linear molecule, all in a line. Last one here, then if we have 6 things around an atom, it's octahedral geometry. And sulfur hexafluoride, as an example, it's a perfect octahedron. So octahedron, you can look at fluoride. Fluoride forms octahedral geometry. Actually, octahedral geometry is the same thing as cubic. geometry, so it has a cubic-like thing. Pyrite and fluorite have octahedral geometry, if you want to see that in Google. And if you have one lone pair, it forms a square pyramid. So square pyramid is like the Egyptian pyramids. So you have a square as the base, and then you have an atom there. That's known as a square pyramid. And if you have two lone pairs, this is known as square planar. So all these atoms are coplanar. Okay, so now let me summarize this, and I'll put my iPad to show you this. Then here is the chart in general. And if you look at this, so maybe I'll flip it again. Sorry if I'm making you dizzy at home. Barrel roll. Okay, so electron groups, this part right here, that means bonding and non-bonding. So electron groups is just things. It doesn't matter if it's single bonded, double bonded, triple bonded, or if it's a lone pair. So if you look at CO2 here, so carbon dioxide, it has two things. It has a double bonded oxygen and a double bonded oxygen. So carbon, the world of carbon sees two things. It sees two bonding groups. So two things, both bonding, that's linear. So then three things. So let's look at these. So boron here sees three things. It's three fluorines, and they're all bonded. So three things all bonded. So sulfur dioxide, it also sees three things. It sees an oxygen, and a lone pair. Those are three things. It doesn't matter that one of the oxygens is double bonded. It's actually a resonance structure. So for three things all bonded, it's planar geometry, electronic geometry, and planar molecular geometry. And then for three things, two bonding, one lone pair, it's planar electron geometry, bent structure, molecular geometry. Now four things, they're all bonding, it's tetrahedral geometry. So all things that has four things is tetrahedral. For the molecular geometry, for four things, all bonding, tetrahedral. For three bonding, one lone pair, it's trigonal pyramidal, so three base pyramidal shape. And then two bonding, two lone pair, bent. I'm going to add another one here. So for if there is one bonding and three lone pairs, so like this example, hydrogen fluoride. So if you look at fluorine, it has a hydrogen and it has three lone pairs, right? So this is linear, but this is kind of obvious though, because it's two atoms. Two atoms have to be linear in geometry. There's no other choice. Okay, so then going on, for five things will always have bipyramidal electronic geometry, molecular geometry. So for all bonding groups, bipyramidal molecular geometry. For one lone pair, seesaw, two lone pairs, T-shaped, three lone pairs, linear. And then octahedral geometry, for all bonding, electronic geometry is always octahedral. Molecular geometry, all bonding, octahedral, one lone pair, square planar, two lone pairs, one lone pair, square pyramid, two lone pairs, square planar. Okay, and this is then the overview of this. There's actually more. You can have other bonding schemes, but in this class we're not going to go beyond 6. It can go higher. There is VSEPR for higher order, but this is it here. So we will stop here for right now, and we will talk about more next time.